You've heard the buzzwords, right? AI, machine learning, neural networks. They're everywhere, running all the tech we use every single day. But how do they actually work? Well, today we're going to pull back the curtain on the basic building block of all modern AI. We are going to demystify the neural network.
Okay, so take a look at this. It's a 3, right? Of course it is. Your brain knew that instantly. Didn't even have to think about it. It doesn't matter that it's sloppy or kind of low res. You could recognize a 3 in thousands of different handwriting styles. For a human, it's just incredibly easy. But now, stop and think for a second. Imagine you had to write a computer program to do that same job. How would you even start? You'd have to write rules, right? Like a 3 has 2 curves. But what if it's written with sharp angles? You'd have to define what a loop looks like, where it should be, for every single possible variation. The task suddenly goes from super simple to almost impossible.
So what's the solution? Well, here's the brilliant part. You don't program the rules at all. Instead, you build a system that can learn the rules on its own, just by showing it thousands and thousands of examples. And that right there is the core, elegant idea behind a neural network.
So how do you actually build a machine that can learn like that? The answer is surprisingly cool, and it's kind of inspired by how our own brains work. It's all about breaking a really big problem down into a network of simple layers. Think of it like an assembly line for recognizing things. The very first layer doesn't see a 9 or a 3. It just sees a grid of pixels, light and dark spots. That's it. But then, the next layer in the line looks at those pixels and learns to spot really simple patterns, like little edges or short curves. Then, the layer after that takes those simple edges and combines them into bigger ideas, like a full circle or a long straight line. And then finally, the output layer puts all those pieces together and makes the final call. Okay, I see a loop on top of a straight line, that's got to be a 9. See? Each layer gets a little more abstract, building on the work of the one before it. And here's what that whole structure looks like in a more formal diagram. Now, it might look complicated, but the idea is exactly what we just talked about. Information flows in from the input, it gets processed through these hidden layers in the middle, that's where the real thinking happens, and then it comes out the other side as an answer. It's this flow that lets the network figure out the puzzle.
So we've seen the whole network, the big picture. But what about the little tiny units that actually make it up? Let's zoom way in on a single one of these artificial neurons and see how it actually thinks. All right, first up, weights. Every single connection between these neurons has something called a weight. You can think of it like a volume knob that controls how much influence one neuron has on the next. A really high weight means the connection is super important. By turning these knobs up and down, the network learns which patterns it needs to pay close attention to. Next, there's the bias. So after a neuron adds up all the signals it's getting from its neighbors, each one turned up or down by its weight, it adds this one extra number. That's the bias. It's basically a thumb on the scale. A high positive bias makes the neuron really eager to fire, while a big negative bias means it's going to take a much, much stronger signal to get it to activate. So now the neuron has its total signal from the weighted inputs plus its bias. What does it do with that number? It runs it through one final step, the activation function. And this function has a really simple job. It just squishes whatever that final number is into a clean, predictable output, usually something between 0 and 1. It's like the neuron's final decision. How loud am I shouting right now? And when you put it all together, believe it or not, it boils down to this simple-looking equation. The final output is just the activation function, that's the F, applied to the sum of all the inputs times their weights, plus that final bias. That's it. Billions of these tiny little calculations, all happening in layers. That's how a neural network thinks. So for that simple little network we talked about, the one that recognizes handwritten numbers, how many of those knobs and dials, those weights and biases, do you think the computer needs to tune? Almost 13,000. Every single one has to be adjusted just right for the whole thing to work. That's what we mean when we say a network is learning. It's finding the perfect setting for all 13,000 of those dials. And the ability to automatically tune those thousands or even billions of parameters is exactly what sparked the deep learning revolution. Decades of theory suddenly slammed into a massive increase in computing power, and that changed technology forever. But this revolution didn't just happen overnight. The core ideas actually started way back in the 1950s. The real magic started to happen in the 80s with an algorithm called backpropagation.
that finally let networks learn from their mistakes efficiently. Then in '97, we got networks that could remember things. But the spark that really lit the fuse was in 2012. A network called AlexNet used the power of modern gaming computer chips, GPUs, to just absolutely shatter all the records in a huge image recognition competition. That was the moment. That was the beginning of the AI boom that we're living in right now. And that brings us to today, because this isn't just some fascinating lab experiment anymore. It's the engine that's running quietly in the background of pretty much our entire digital lives. I mean, seriously, every time you talk to Siri or Alexa, that's neural networks. They're being used in medicine to spot cancer in medical scans better than humans can. They're in finance sniffing out fraud, and in science discovering new drugs. They power the recommendation engine that tells you what to watch next on Netflix. They do the real-time translation in Google Translate, and they're even making weather forecasts more accurate. They are, quite literally, everywhere. And this quote really just says it all. The basic architecture we've been talking about, the simple idea of processing information through layer after layer, that's the foundation for pretty much all of the most advanced AI systems on the planet today. From our little number recognizer to the most powerful models in the world, the core principle is exactly the same. So we've gone from the simple puzzle of recognizing a handwritten number to a technology that can translate any language, see the world, and even help design new medicines. And it all comes back to this one idea: building layered networks of simple little neurons and just letting them learn from data. It really makes you wonder, if they can do all that today, what incredible problems are we going to teach them to solve next?